Section 8.2 is a fairly lengthy section about composite functions and inverse functions. So we have 5 topics to cover. Number 1 is to find the composition of functions and express certain functions as composition of functions. And then we find the inverse of a relation if it is described as a set of ordered pairs or as an equation. Then, given the function, we can determine whether it's a one-to-one and has an inverse that is a function, and then to find a formula to find the inverse of a function if it exists, and then graphing inverse relations and functions. And last but not least, determine whether a function is an inverse by checking its composition with the original function. So the first topic would be the definition of a composite function. So the composite function f of g, the composition of f and g is defined as composition of f and g of x, is a function of g of x. In other words, the input to the function is another function, that's g of x. So here's a visualization of the composition of functions. So here are the inputs x, and here's our function g, like a machine, and out comes g of x, and that output is the input for the function of f. In other words, now the output is f of g of x, since g of x is the input for f. This may be a useful picture because people can visualize things a little bit better than just an abstract description. And so that might be something you want to look at and see if it makes sense to you, and I'm sure it does. It's a good way to visualize what a composition of function means. So the composition of f and g of x means that for the function f of x, we replace x with g of x. So in other words, this then becomes x squared minus 1. It replaces our x in this function here, plus 5. So that then is x squared minus 1 plus 5 would be x squared plus 4. Now, the other way around, the composition of g of f of x means we look at g of x and we replace x with f of x. So here is an x squared, that means we need to square x plus 5. So that means it's equal to x plus 5 squared, so we replace x with x plus 5, we square that quantity, minus 1. And that's equal to x squared plus 10x plus 25, that's this expression evaluated, minus 1. So then the final answer is x squared plus 10x plus 24. So here's a guided solution. Given f of x equals 4x plus 5 and g of x the third root of x, find the composition of f and g of x and the composition of g of f of x. So first, the composition of f and g of x. That means now g of x is the input to the function f of x. So now we replace x with the third root of x, because that is g of x. So that means we have 4 times the third root of x plus 5. Similarly, the composition of g of f composite of g of f and x. So now f of x is the input to g of x, and so since since f of x is 4x plus 5, we now replace the radicand that was x now is 4x plus 5. So the third root of 4x plus 5. 4x plus 5. In the next exercise, we are asked to find f of x and g of x such that h of x is a composition of f of g of x. And the answers may vary, there are different possibilities. But, for example, we could say that f of x is equal to so we could say f of x is equal to the third root of x, and g of x is equal to x squared plus 1. Then the composition of f and g of x would be equal to the third root of, remember we replace x now with g of x, so it would be the third root of x squared plus 1. Which is equal to h of x. And for the b part, we could choose, for example, f of x. Let's say f of x is equal to 1 divided by x squared. And we could choose g of x to equal 1 x plus 5 rather. X plus 5. Then h of x, the composition of f and g of x, would be equal to 1 divided by x plus 5 squared. Because now we replace x with x plus 5, since it's a composition. Next, we'll be discussing inverses of functions. And first of all, we talk about inverse of relations, or ordered pairs. And by interchanging the coordinates of the ordered pairs in a relation, we produce the inverse relation. For example, when we have the relation G given by the ordered pairs 2, 5, minus 1, 4, minus 2, 1, so we have the ordered pairs given here as 2, 5, and minus 1, 4, and minus 2, 1. To find the inverse and its graph, we simply exchange the x and the y in the given ordered pairs. In other words, we can say the inverse of G is a set of ordered pairs 5, 2, 4, minus 1, and 1, minus 2. And when we plot those, we get 5, 2, so it'd be this one here. And 4, minus 1 would be here. 4, minus 1. And 1, negative 2 would be right here. So these points represent the inverse relation from the original function or relation G. So the previous example was an inverse relation for ordered pairs, and now we're going to look at an inverse relation for an equation. So if a relation is defined by an equation, interchanging the variables produces an equation of the inverse relation. To apply that, we have an exercise here. Find an equation of the inverse relation, then complete the table and graph both the original relation and its inverse. So the original relation is y equals 6 minus 2x. And so here is the table of values. When x equals 0, then y equals 6. When x equals 2, then y equals 2. And when x equals 0, then y equals 0, then x equals 3, etc. X equals 5, y equals minus 4. So like we've always done. So by interchanging the variables, then the inverse is x equals 6 minus 2y. So now when y is equal to 0, x is equal to 6. And when y is equal to 2, then x is equal to 2. And when y is equal to 3, then x is equal to 0. And when y is equal to 5, then x is equal to negative 4.